Okay, so this little lecture is about some interesting phenomena that are connected with sound, in particular the Doppler effect and ultrasound.
Understand. The first one is a Doppler effect. Um, if you all, played with Matchbox cars or a kid or watched your siblings do it, you always make a race car sound, right? What does a race car sound like? It sounds like vroom, right? So what's going on there? Well, notice that when you do the vroom, vrr, it's at a high frequency, and the is a low frequency, right? Vroom. Um, and that's the Doppler effect. And the Doppler effect results from the fact that the source of a noise is moving, and so that an observer is going to hear those sounds differently, right? So if this car isn't moving and is making a noise, it's going to produce sound waves that go out like this. Um, and basically, these waves are all traveling at the same speed, so the distance between these two peaks is going to be the same over here as it is over here. But if that car is moving towards the girl here, um, at point 1, this sound wave was made, and that's moving through the air. At point 3, this sound wave was made, right? And at point 5, this sound wave was made. And so when this girl hears it, she's going to hear a wave whose peaks are closer together than when the boy over here hears it. He's going to hear it with the waves that are farther apart from each other. And so that compression of the waves because of movement is the result of the Doppler effect. She's going to hear a wave that sounds like it has a higher frequency than he does, because these are moving at the same speed, but has a smaller wavelength here, or appears to have a smaller wavelength. And that's going to make it a higher frequency sound. So that's the vrr, vrr of vroom, and this is the of vroom, right? Okay. So if a source and receiver are moving closer, the waves will be perceived as compressed. And this is important, that they can either be the source or the receiver that is moving, like the observer or the producer of the sound. And if they're moving away from each other, you're going to get a lower frequency, longer wavelength wave. To find that perceived frequency, we take the frequency of the source, right? And then we take the speed of sound and adjust it with the speed of the observer and the speed of the sources. And the tough thing here is figuring out sign. Okay, so V observer is going to be positive if it's moving toward the source of the sound. V source is positive if it's moving away from the observer. And I won't get too much into why that is, but if you wanted to spend some time, you could figure out why those things are true. Because this is, if this is positive, it's going to increase the frequency of the observer, right? And so that's why that's a positive number. So this is our catch-all equation for the Doppler effect. So what happens to this equation when the observer is standing still and the source starts to approach the speed of sound? Okay, that is, it starts to, the reason this is negative, it's moving closer to the observer at the speed of sound. Well, what happens is what happens here. So you have the red dot and it produces a small sound wave. As it's moving here, just like that car, it's going to produce a sound wave at each point. So this is the one it created at the origin. This is the second sound wave it created. This is the third and fourth and so on. As it continues to move, see how all these blue lines intersect with each other? That's constructive interference of that sound wave. So all of those waves are building upon each other. And that is going to produce a sonic boom. Okay, so it's basically creating a really big sound wave right here. It's adding all of the sounds that have been created up until that point. And so that's why you get a sonic boom. As a plane approaches the speed of sound, it produces a really loud noise. As you move faster than the speed of sound, this thing happens here, where like here's our point 1, and this is the sound wave produced at 1. Here's 0.6, and you can see because the source is moving faster than the speed of sound, it's actually outpaced what the sound wave at 1, right? This was a sound wave that was created at 1. At this point, this plane is already well past that sound wave. And what it does is it creates what's called a bow wake, okay? And so the constructive interference creates basically a sound wave that takes on a cone shape. And again, this is a 3D shape, even though we're drawing it in 2D. That looks a lot like what's happening with this duck, right? Or with a boat. You can see that you get a kind of main wave that's coming off the bow because because of constructive interference. So that's the way sound works when speeds get larger than the speed of sound. And then finally, I want to say a little bit about ultrasounds, because I think these are really interesting. So ultrasound is just like an ultraviolet wave is a light that is outside the visible spectrum. Ultrasound is a sound wave that is outside the hearable spectrum, so it's above that 20,000 hertz. We can't hear that, of course, but it has all sorts of uses, particularly in medical uses. And so you can use it with a high-intensity ultrasound. You can actually use it to destroy cells. I think we're more familiar with the low-intensity use of it, which can be an imaging tool. And so we're just sort of think about how this works as an imaging tool. Basically what happens when we use ultrasound imaging, we throw some ultrasound waves into the body, and those waves get reflected when the material changes. So say between two organs because of differences in acoustic impedance in the different materials. And so acoustic impedance is a combination of the density and the speed of propagation in a material. And basically when the wave moves between two different materials, the physics of that mean that some of that wave gets reflected back. Okay, so different materials have different acoustic impedance. We can look at bone and muscle and fat and so forth. And so an ultrasound, like a radar in a lot of ways, is going to be able to collect those waves that bounce back and come up with an imaging. Okay, so you have the ultrasound transducer, which is just something that's creating an electrical and interpreting an electrical signal. So it sends a wave in, and then it also collects that wave, and we can make images like this super cool one here. So the resolution of an image that's made from ultrasound is limited by the wavelength of our sound. So we want the higher frequency we can use, smaller wavelength we're going to have. But then there are problems with, if you get too high, you have limits in the range of the device. And so there are trade-offs with resolution. But just to give you a sense, if we have a 7 hertz scanner, we can take the speed of propagation within body tissue, divide it by our frequency here, which is 7 megahertz, and you get a resolution of about 1/5 of a millimeter. So that gives you some idea of about the best kind of resolution we're going to be able to get from an ultrasound, at least at this point. It's also interesting that we can combine ultrasound with Doppler effects to actually look at what's moving inside a body. So if you wanted to know, for instance, how effectively blood was moving through a vein or through the heart, you can do ultrasound and take into effect not only the what we're getting from ultrasound, but also the changes in the frequency that can result from things moving within the body. All right, so that's our introduction to sound and our last lecture of the semester. All right.